Good day, class. So, for this recording, I'll be discussing the first sample problem for the second set of unit operations processes that we have discussed last Tuesday. So, the topics actually include gas absorption, stripping, extraction, leaching, and membrane separation processes. So for membrane separation processes, you just have to refer to those principles and concepts related to the different membrane separation processes. You will not be anymore tackling the problem solving part. As for gas absorption, stripping, and leaching, I will be discussing a sample problem for each of those topics, but after each sample problem, I will end the recording. That way, it will not take so much time in uploading later. So, at the end of each topic, I'll be stopping the recording and then I'll be giving another sample problem. Now, for the first sample problem, it's water from an oil installation containing 8 milligrams benzene per liter of water. So, as you can see, water here is contaminated with 8 milligrams benzene per liter. So, it should be reduced to 0.4 milligram benzene per liter through stripping with air at 2 atmosphere. So, in here, you could see that your solvent is air at 2 atmosphere. Now, your problem requires that you determine the minimum amount of air, that is cubic meter of air per cubic meter of water, and then determine how many equilibrium stages would be needed for optimizing the process. So for this sample problem, we need to go to our whiteboard. So I'll transfer to the whiteboard now. And we're here. So we'll start with the given, though we have started already with the solution of this in class. We'll start again, that way uh, you can have one thorough understanding of the problem from the very start. So we need to write our stripping column. So let's say we'll have a rectangle for that. We know for our gas absorption and stripping processes that we have two phases contacted. So we have the gas phase. So in this case, this is V1, and this part of the tower is labeled as 2, so we'll have this as V2. Then we'll have our liquid here, L2. Oh, sorry for this one, the arrow here. Oh wait, so the arrow here should be pointing downward. So this is L1. Okay, and this is the part of the tower, which is 1. So since our solvent is pure air, so y1 then is equal to 0, and this is at 2 atm. Then we know that in here for V2 we'll have y2, and for L2 this is the corresponding initial concentration of benzene per liter of water, and it has to be reduced to zero point 0.4 as what we have read a while ago, zero point 0.4 milligrams benzene per liter of water. For our required information, we need V1, the amount of the solvent V1, and that is cubic meter of air. Let's say if you're using 1 cubic meter of water. And then for letter B, we'll have the optimum number of stages. So this will be our simple representation of what the problem gives us and what it requires. So let's go to the solution. So if you notice, our concentrations are in mass per unit volume, so there's a need for us to convert it to moles, because when we speak of gas absorption and stripping processes, our concentration should be in mole fractions, and as such this will not work initially, so there has to be a conversion. So for 2, or for stream 2, we need to determine the number of moles of benzene, and in that case we have 8 milligrams benzene, and we convert it to 1000 milligrams to 1 gram, and then we'll have 18 grams for every mole. So this is 1.0256 times 10 raised to negative 4 moles of benzene per uh, liter of water. So we'll have also moles of water. So we'll have, since we already use 1 liter of water here, so that we'll have to consider only 8 milligram mass for benzene. So for 1 liter of water, we just need the density of water to convert it to mass, and then mass to moles. So we'll have 1 liter for there's 1000 ml for that. Water is 1 gram per ml in density. Then molecular weight is 18 gram per mole. So you notice we get to cancel the liter unit, the ml unit, and the gram unit. Here on top, we get to cancel the milligram and the grams, giving us the mole unit. So for water, we have 55.5556 moles. So we already have the number of moles of each of our components, so we can determine, in this case, x2, because we're considering the upper part of our tower or column. So for x2, that would be moles of benzene per the total number of moles. So that should be 1.84607 times 10 raised to negative 6. We do the same procedure for stream 1, and for stream 1, number of moles of benzene is zero point 0.4. So we'll not anymore write the units, we'll just follow to the conversion here. So zero point 0.4 divided by 1000 and then divided by 18. This will give us the moles of benzene, which is 5.1282 times 10 raised to negative 6. Then for water, it's still a liter, so it would be the same as this one, because this one is zero point 0.4 milligrams benzene per liter of water. So we'll just have to copy, because it's the same amount for every liter of water. So that has 55.5556 moles. So in here we'll have x1, so same thing as in here. So 5.1222, or 1 2, I think this is 82. Sorry, we'll just write again. So you'll have 1000 here. This is 5556. So 5.11282 times 10 raised to negative 6 divided by 5.1282 times 10 raised to negative 6 plus 55.5556, giving us an x1. I'll just write in here, equal to 9.2308 times 10 raised to negative 8. So we have converted the concentrations and mass per unit volume to mole fractions now for x2 and x1. So it would be better that at this point you're going to get a screenshot or a picture of this part of our solution. That way when we go to the next page, you have something to refer to in terms of the values that we have acquired already. Okay, so now we go to page 2. Okay, we'll just go here. So that would be our next page. This is our next page already. Next thing we do is, since we are to determine, if we go to page 1, let's go back to page 1 of our solution. This is our page 1. We are to determine the amount of solvent per cubic meter of water. So we'll use this basis, 1 cubic meter of water. Okay, so for every 1 cubic meter of water, we will determine the corresponding number of moles of water in that case. So for next slide, so if we have 1 cubic meter of water, this is for your L2. So you'll have to convert that to using density of water. We'll have 1000 kilograms in 1 cubic meter. Then we convert 1 kilo to grams, so that would be 1000 grams. And then again, we'll have the molecular weight of water. That way, we can determine L2 in terms of the number of moles. So this is 55.5556 moles. This represents already your L2. At the same time, this is also our L prime, the inert part of our liquid phase where we need to strip off benzene from. So this L2 is also L prime, and that's 55.55556. Actually, this is not the entire L2. This is just the number of moles of water in L2, but it's not the entire L2, because L2, if you notice, has 8 milligrams benzene. So we'll just place here from L2 because it's not really the entire thing. Okay, so that's our L prime. If we do component balance using inert streams, okay, so you'll have L prime, and you have x2 over 1 minus x2 plus v prime. We'll have y1 over 1 minus y1. We'll have again L prime, this time x1 over 1 minus x1, and we'll have v prime, this time y2 over 1 minus y2. Now, since our solvent here, which is air, does not contain the benzene, so automatically this part is 0. Now, if you notice in here, we already have x2 and we have x1. The remaining part that we need to determine is this, the y2. So how do we determine y2? So using Henry's law, we know that y2 is equal to mx2, and if we'll associate this with Henry's law, this will be h, the Henry's law constant, divided by the total pressure of the system times x2, and this is our y2. So from table 2-22, page 2-89 of your handbook, this time the 9th edition, you'll be able to get for benzene an H value of 299 atm per mole fraction. So using this, we can determine already our y2. So we know already x2, so y2 will just follow. So I'll just place it here to make use of the space. So y2 is equal to your 299, the constant, we divide by the total pressure of the system as it enters the column. That's 2 atm, and we have here x2, the x2 that we have computed a while ago, which is 1.84 607, 1.84607 times 10 raised to negative 6. So you'll get a y2 value in this case of 0.0002760. Now, since you already have y2, then you can go back to this particular equation. Let's say this is our equation 1. So if we go back here and substitute everything, we'll be able to find the V prime. And that's the air that we need to use, that we will get the indicated recovery for benzene. So let's go to the next slide for determining the V prime. So we just substitute actually. Okay. So if we substitute in equation 1, so from 1, substituting, you have for L prime, you have 55.5556. Then we multiply it with 1.84 times 10 raised to negative 6 over 1 minus 1.84 times 10 raised to negative 6. So you have this on the left side. Another L prime here on the right side, but this time you multiply with x2, x1 rather, so that would be 9.2308 times 10 raised to negative 8. So you'll have 1 minus 9.2308 times 10 raised to negative 8. Now, on the second term here on the right side of our equation, we'll have the V prime, which needs to be multiplied to 0.0002760. This is taken from our answer a while ago. I'll go back later to that particular page. 1 minus 0.0002760. So in here, you'll be able to get the V prime, and that's the air that enters the column to take out the benzene from water. So this is your V prime. And we will know the volume. Remember, this V prime is just the air that was used as a solvent for the water that needs to be stripped of benzene. So in terms of the volume, because this one is moles and what the problem is asking for the volume, we can assume ideal behavior for our air. So we have PV equal to nRT. We want the volume here. So volume is equal to nRT over P. Now substituting, the n that you will be using here is the n that we got in here, the V prime. Oh, sorry. This should be 0.3529. So that would be for the n. This one we use the n, then we use the r, 0.08206 mole liter per atm Kelvin. Then we have the temperature, which is assumed to be standard room temperature, so you have 298 Kelvin. So we get to cancel the Kelvin unit. This is actually mole, so we got to cancel wait lang, so mole, and then I got the units here interchange, so this should be mole, liter atm. So liter here atm per mole Kelvin. Okay, so we canceled already the Kelvin, so the remaining unit to be canceled is the mole, and we need to multiply by the this is your nRT, so we need to multiply this by the 1 over P, or division by P. So our P in this case is 2 atm. So if you do dimensional analysis, you're just getting rid of the unit that your units that are not important, or that shouldn't be the unit of the variable that you are trying to find the value of. So you have a V in volume already of 4.3148. So this will be cubic meter of air. This much air is needed to reduce the given concentration of benzene in water. So this is per cubic meter of water. Okay, so this is the first requirement of the problem. What is the V? Or this is actually based on our column, this is already our V1. Okay, now for stripping to be maximum, the solvent require, or for stripping to be at a minimum solvent requirement, we're going to make use of the x2 that we have determined a while ago in the equilibrium equation. So use x2 in the equilibrium equation. So let's get to the next slide. You may take a picture of this. So we'll use this one. Now for minimum solvent requirement, what you're going to do is first use the equilibrium equation so that you'll be able to determine the maximum amount of A, and that is our benzene in the upper part of your column, or what's the maximum amount of benzene that is recoverable. So Y2 max, this refers to the uh, gas, the concentration of the gas leaving our tower, because our solvent this time is gas, so that is why it's Y2 max. So if we use the equilibrium equation, it would be like this, and you have your M to be 299 divided by 2. So the slope M of the equilibrium curve is actually your constant, your Henry's constant, which is 299 divided by the total uh, pressure of the system as it is being processed in your column. So 299 divided by 2, and we make use of the x2, which is 1.84607 times 10 raised to negative 6. So you'll get a y2 maximum value of, so how many zeros? 3 zeros, and then 22760. Okay, now you have the y2 maximum. So we know also that our v prime, the v prime that we solved in the previous page, is already our v minimum. So your v prime, the computed v prime, is already your v prime minimum, and that's 0.3529. For optimum solvent requirement, we need to multiply this by 1.5. So V optimum, the optimum amount of air that should be used, is equal to 0.0, oh sorry, so 0.3529, no more zero, so 0.3529, and since this is your minimum, and then you multiply it by 1.5. So this is your minimum, the 0.3529, this one. So we just copied it and multiply it by 1.5. So that would be now, or this will be now, your optimum solvent requirement for your system so that the desired recovery is achieved. So wait lang. So we have V optimum 0.3035. So you have 0.52935 moles. So that's your V optimum. Now we will determine then V2, the amount of gas leaving the tower, our solvent gas, and that's it. And it's equal to, so you have 1.0256 times 10 raised to negative 4 minus 5.1282 times 10 raised to negative 6 plus 0.52935. So this is just simple material balance. Okay, so you will have uh, 1.0256 times 10 raised to negative 4 plus 5.1282 times 10 raised to negative 6, and we have 0.52935. So your answer for V2, this is the final gas phase that leaves the tower, is equal to 0.5294. Okay, 0.5294. Okay, so this one, this is the moles of benzene entering. The 5.1282 is the moles of uh, in V2 you have 1.0256 plus 5.1282 times 10 raised to negative 6. The first one is negative 4 plus 0.5239. So giving you a V2 which is 0.5214. The reason why you need V2 is because you need to get the gas absorption factor for the bottom and the top of your column. So this is your V2 now. You'll need this in one absorption factor, and that is at the top of your column. Okay, we'll add another slide. Okay, so as for the gas absorption factor A1, so that would be L1 over MV1. And your L1 a while ago is 55.556 plus 1.0256 times 10 raised to negative 4. And we divide it by the mass, but not the mass, but rather the slope of the equilibrium curve, which is 299 divided by 2, and then we multiply it with the V1 we solved a while ago using this set of slides. So 52935. Now in this case, you will have an A1 value of 0.7020. You do the same for A2, so you'll have L2M V2, so we can compare whether they really deviate much. The value is really deviating much. Okay, you still have in L2 the 55.5556, this is for the water, plus 5.1282 times 10 raised to negative 6. So that's your L2. For the slope, the same as one on top, but this time you're going to multiply it with 0.52935. So you'll have an L2 value of 70 or 0.7019, almost the same. So and here we'll now go to determining the geometric mean. So you have A1 times A2, and then the product you take the square root of. In this case, it's just multiply these two and take the square root of the product. You'll be getting 0.70197. I think you know already the next step here. All you have to do is determine the number of stages. So go to the next slide. We'll add one here. So your n optimum, since it was based on the minimum, we multiplied it with 1.5, and you still make use in this case Krimster equation. And since this is stripping, you'll have x2 minus y1 over m over x1 minus y1 still over m. You multiply it with 1 minus a plus a. So this is your numerator, the entire numerator over ln of 1 minus a. And this is your stripping factor. The opposite of the gas absorption factor is the stripping factor. So substituting everything, by the way, you have an ln here. So it will be ln of since y1 is 0 because we have pure air as our solvent, so this is 0. So you'll have x2, the x2 that we have computed, 1.84607 times 10 raised to negative 6. We divide it by 9.238 times 10 raised to negative 8. And then we multiply it with 1 minus the 0.70197 for the gas absorption factor geometric mean. And here in the denominator, you have ln of 1 divided by 0.70197. So your n optimum in this case is 5.3593 stages. So this is the second requirement, the optimum number of stages, which required you to first get the minimum solvent requirement, multiply it by 1.5, and then the rest you use the Krimster procedure, of course with the Krimster equation. So this is the last part of our discussion here. This is the n optimum, the theoretical number of stages. Okay? Okay, we'll stop our recording for now so that we can proceed with problem number 2.